I've only been here for about a little less than 24 hours, so I hope to make a longer visit at another time. But I'm really pleased to be able to talk about what we're seeing from the National Science Foundation in the U.S. in terms of the directions that science and engineering are taking, particularly driven by computing and increasingly driven by data. Data are consuming us. As you notice from your email inbox, you will find you are getting many more messages. I once had an issue. I was getting so many emails, and suddenly they weren't appearing in my inbox anymore, and I wondered why. And then I noticed I had exactly 32,768 messages in my inbox. And it turns out, of course, that no one had ever thought that you could have more than that in your inbox, and so it didn't allow more than that. So if I started deleting them, the new ones were actually appearing, so they were held in some internal buffer. But that's just an indication of one example of the kind of trends that we see, where science is being dominated by not only data, but also increasingly by collaboration. So, of course, you get more emails because you're working with more people, and it increases our ability to work together. And so those are two trends that I hope to really highlight here as we go through my lecture tonight. So I'd like to start then with a little bit of a compressed history of science lesson to point out how things have been changing very rapidly in the last couple of decades, but not very much for many hundreds of years before. So one of the key points of my entire lecture tonight is that there's almost a step function in the change of the way science is being done, not only in terms of the methodologies, but in terms of the culture. So if you were to look back in time, back about, say, 400 years ago to the time of Galileo and Newton, you find that at that time, the style of doing science was collecting data. So at that time, there were observations by people like Tycho Brahe and so on, telling about the observations of the solar system. And from that data was derived ultimately a theory of gravity that stands today, at least within some limits, the Newtonian theory of gravity, but really ushered in by people like Galileo and Newton. But look at the kind of science that they did, the way they did it. So they took data in notebooks, and then if you were to digitize that, you'd find probably it's of order kilobytes of data. They worked in very small teams, either completely alone or perhaps with a student, and that style of doing work was then passed down generation after generation after generation until very recent times. If you were to think about the kind of amount of arithmetic they could do, if you're very good at arithmetic and mental arithmetic, you might be able to do something like a floating point operation per second, something like that. You could do it. That's probably a little bit more than you could really do, but nonetheless, that's about where a single person can work. Now, fast forward 350 years to 400 years, and I'll start off with a modern-day approach to science illustrated by work by Stephen Hawking. So in the same area of science, Stephen Hawking worked out theoretically what would happen when two black holes collided, and there's a diagram there. Time is going up, and the two black holes are coming together, and they collide, and the event horizons merge at that time. And so Hawking worked out in a theoretical way, this is actually a direct scientific visualization, let's call it, a hand-drawn sketch from one of his papers around 1972. And again, if you were to digitize that and think about the style of collaboration, it was still more or less along the lines of the way Newton and Galileo worked. Something like kilobytes of data, people working more or less individually or in rather small teams. But then just from that period forward, in this one field of general relativity only, and this is an area that I think has been one that has been dominated, gravity and general relativity have been dominated by mathematical approaches, by people working more or less in isolation, and it's now exploding as every area of science and engineering are in the terms of the number of people that are working on problems and the kind of computation and data that are being generated in general relativity. So fast forward about 20 years, and you see a simulation of two black holes colliding. This is a simulation carried out by my group in collaboration with the group at Washington University. So we had a collaboration of people who had to know about how do you solve Einstein's equations on computers. You had to know about numerical methods for PDEs. You had to know about parallelization, scientific visualization, and so on. So the kind of expertise you need to integrate to solve a single problem like this is much larger. So at that time, we had a collaboration of about 10 people at two institutions working together using a rather large computer, probably one of Ralph's computers at that time, Probably was a Cray C90, I would imagine, at that time, something like that, and generating data of order about 50 megabytes. So we're up to about 1,000 times as much data being generated as just about a decade or two before, which is typical. And so, however, just go fast forward a few more years and actually do not only the axisymmetric calculation, which is the one in the middle, but the full three-dimensional calculation of two black holes colliding. That brings in many more degrees of freedom, much more complicated. This was run on a machine with many more processors. In fact, in this case, this is a 256 processor SGI Origin 2000, a larger group having much more data to deal with. In fact, it's 1,000 times more data output. So although we typically focus on flops, floating point operations per second as the measure of a supercomputer, we're also having to deal with enormously larger volumes of data that come out. And so, in fact, we had people working for many, many weeks to visualize a single simulation. And in fact, I actually had to fly people from Berlin to Champaign-Urbana, where the visualizations were carried out. Then the data were carried back on disks because it was really more than it was really practical to transport over high-speed networks. And the work continued in Berlin. And in fact, through the visualization process, we discovered a couple of small errors in our code. But it took many, many weeks and actually months of visualization in order to really understand that. So the process of analyzing the data that comes out of these type simulations is also increasingly complicated, and rather larger groups are needed. So fast forward a little bit further to the present day. There is now a rather large community of scientists working around the world. And in fact, there's this development called the Einstein Toolkit, which has people from about 17 sites, 9 countries, over 50 members of this collaboration that are particularly working to develop the software infrastructure to enable simulations of two black holes colliding. And that allow everything from advanced adaptive mesh refinement to parallel layers that are needed for I/O and so on. And so I will show you a visualization of a simulation that was carried out by people at the Max Planck Institute for Gravitational Physics, led by Luciano Rizzola at this time. So let me see if I can. Let's see. All right. So these are different levels of refinement. So we're going to zoom in. So the space-time is rather large, but we're really interested in where the black holes are. And you can see them right here. But we're also interested in how the waves that propagate out far away. So these are two black holes, and I'll show them in evolution in just a minute. But the point is, we have to resolve the areas around the black holes, which are relatively small, and they have a very high gradient gravitational fields around them. So you need a lot of refinement around these regions. And then we want to then follow the gravitational waves that are generated by the black holes as they coalesce. So this is a system of two black holes in a binary pair that are orbiting around each other. And I'll show you in a minute. This is just showing the initial data. I'll show you the evolution. But the point is that this collaboration has generated very complex systems of software and a lot of numerical expertise that's built into this, that we can now do simulations like this that I spent most of my entire career trying to get to. So in fact, in my career, I was able to get up to about one orbit of two black holes colliding, but now the entire field is broken open because of this collaborative approach where people can share numerical methods and algorithms and even software libraries and so on. So it is now routine that people can do many orbits of black holes, and that's really what we expect happens in real-life astrophysics. So this shows not only how the black holes have coalesced, but it shows the gravitational waves propagating out with a mesh, a numerical mesh that has something like 9 levels of refinement, so that we don't need to refine the area far away from the black holes, but we do very near. And so we have these embedded meshes that allow the kind of simulation to be carried out on computers that it just would have been absolutely unthinkable to do simulations like this just a few years ago. So this is just sort of zooming out, and you can see the entire far boundary far away so that the waves are propagating out. And then you could imagine in your simulation, if you only had a detector there, you might actually see these waves. Now, gravitational waves have never been observed. They've only been predicted theoretically. So another part of what's happening in general relativity is a set of experiments that are aiming at detecting these waves. But in the meantime, this field has completely exploded because through the use of high-performance computing and advanced software development and teams of people working together applying new kinds of methods and new understanding of hyperbolic systems of equations and so on, I would say that computational science has really allowed a breakthrough that allows us to solve Einstein's equations, which we had for nearly 100 years before they could be solved in the rather general case here. So it's a breakthrough. I think it's a really fundamental breakthrough in fundamental science physics that this is now possible. And it's because of these two trends of computing increasing exponentially and large collaborations. But we'd actually like to not only simulate this, but detect these waves that have been predicted by Einstein back in the early 1900s. They've never been detected before. So after a century, we just now have the ability to solve these equations, and we also just now have the ability to detect the waves that Einstein predicted would be emitted when things like two black holes collided. So I show here pictures of the two detectors that are actually funded by the National Science Foundation in the United States to detect these waves. This is a very large experiment. I won't go into the details, but I'll tell you it is an instrument the size of downtown Abu Dhabi that is 4 kilometers in each direction, so maybe perhaps the island that I visited today. And when waves come through, it changes the actual size of these two arms of laser beam. So the laser beam goes back and forth inside one of these arms and another one in the other one. And what happens is when a wave comes in, it stretches, compresses one of the arms and stretches the other one. So there's a little bit of a difference in the path length. And when the waves from the laser beams actually interfere with each other, there may be a change in the interference pattern because of the gravitational waves. And it's an unbelievable experiment because if a supernova blows up in the far part of the galaxy and sends waves 100,000 years later that come to the Earth, that will cause this instrument, which is 4 kilometers on a side, to oscillate something like the distance much less than the diameter of an atomic nucleus, and that is detectable with these detectors, so we think. So we are looking forward in the next few years to actually being able to detect these waves. And we're also looking forward to then being able to, from those detections, determine what has happened out there. Was it two black holes colliding? Was it a black hole and a neutron star? Was it a supernova? Or was it something that we wouldn't have expected at all? So these are the kind of things now that you see in a rich interplay that's just beginning between experimental gravitational physics and numerical relativity, where people are beginning to simulate things that should be seen by those detectors. And once they're detected, then there will be a signal back to the theoreticians. Can you tell us what this signal means? Is it two neutron stars, or what is it? And so the people go back and simulate things. And there are many, many things we'll be able to look at that are not visible in any other form of radiation that we know of right now. So we expect to have a much deeper understanding of the universe as a result of this. So to kind of close off this particular part of my talk, I just want to say that I think there's a new era of science that is really emerging after a century of having Einstein's equations, but not being able to solve them and not being able to detect the waves of gravitation that were predicted by Einstein. And a century later, the technologies, both in the computing side and on the experimental side, have matured at the same time. So it's quite an exciting, and it's really an amazing coincidence, actually. Now, look ahead a little bit further. So I've only talked about gravity and general relativity, but in the real world, we have more than gravity. We have fluids, we have magnetic fields, we have all kinds of things. And so if you want to look at more and more complex problems, for example, gamma ray bursts are bursts of gamma rays that come from distances well across the cosmos, and they generate more energy than comes out of entire galaxies for very brief periods of time. We don't really know what they are. There are some models, but we do know that in order to understand this, we'll have to know about not only general relativity, but hydrodynamics, nuclear physics, radiation transport, neutrinos, magnetic fields. Each of these areas of science is really locked away in an entire community that doesn't really interact with those other communities very well. And so we need to find ways to integrate all of this expertise in order to solve single complex problems, like in this case, what is a gamma ray burst? If you were to do all of the arithmetic and work out how much it would take to actually do all of these kinds of science integrated into a single problem, you can easily convince yourself you need petaflops, 10 to the 15th, I think it is, floating point operations per second sustained for weeks at a time in order to carry out simulations like that, even on highly adapted meshes where you have something like 9 or 15 levels of refinement. In fact, I worked this out once. So you can saturate, basically, you can saturate any supercomputer that's coming in the foreseeable future, even with the most advanced algorithms that we've been able to develop in the last few years. And many problems are like this. But also, they also generate petabytes of data coming out. Now, petabytes of data, this is, again, factors of thousands and millions, actually, factors of millions more than the simulations I showed you before. So we are in a new era where we really don't know how to handle the amount of data. We don't know how to process it. We don't know how to find features in it. So I think this will be driving actual fundamental mathematics in terms of feature extraction, statistical mathematics as well. And so there's a lot of work to be done, even on a theoretical level, not just on the cyber infrastructure. What do you do with the data? How do you manage it? How do you transport it? So we have to have advances in all of these areas. But I think the thing I really wanted to point out is that this area of general relativity and gravity, which for 4 centuries really didn't change very much except theoretically in the early part of last century, but in terms of the methodology of science, it didn't change much. There's been a step function of 10 to the 9th to 10 to the 12th in terms of the amount of data, the amount of computations that are needed, and the collaborations have expanded dramatically. And this is an area that for many years was dominated by a single scientist working in isolation. So the point is the culture of science has changed dramatically as well. So now we're getting into the realm of general relativity being very important for not only understanding space-time, but as an ingredient in relativistic astrophysics more generally. And so at the same time as all of the theoretical work is going on and we're able to generate all these data coming out of simulations, we're developing an array of instruments around the world. And so, in fact, there are radio astronomy telescopes and the extended very large array, a thing called ALMA in the Atacama Large Millimeter Array in the Chilean Atacama Desert. In the South Pole, we have an experiment called IceCube that is detecting neutrinos from distant sources in the galaxy. On the horizon, we're building new optical telescopes, 24 to 42 meter telescopes. These will be completely digital. And there's a possibility that we may have one of our LIGO detectors for gravitational waves actually deployed in Australia. All of these things will be generating petabytes of data, and they're distributed around the planet. And any one of the researchers that needs to look at these things will be not at one of those sites, certainly not at all of them. And so we need to think about how we transport the data, how we make it available. And these are volumes of data that are way, way beyond anything we've actually tried to deal with up to now. So I don't know if you can see these images, but it shows that a sort of a growing number of different activities and experiments that are going on around the world. And there's one thing in particular, I'll come back to this in a minute, but there's a new telescope that's being deployed called the Large Synoptic Survey Telescope, or it's actually a project that's been proposed. And probably within the next decade, if it goes forward, it will be generating an incredible amount of data. So some of you might be familiar with a thing called the Sloan Digital Sky Survey, SDSS. In the last decade, it's an astronomy survey project that generated about 40 terabytes of data for the world astronomical community. And there are an enormous number of papers that have been written just on that data set. There's far more data than we have astronomers to analyze all of it. And so this in a decade generated 40 terabytes. The LSST will generate that much data every single night. And we'll take pictures of the sky every single night for 10 years. And so 40 terabytes a night, and that's before it's processed. So again, it's like compressing an entire decade of astronomy output into one single night, and that's what's coming up. So it's really, by many orders of magnitude, beyond our experience base up to now. So anyway, let me go back one slide. Whoops. Oh, sorry. Okay. I just wanted to point out the last thing. When something goes off, so neutrinos are detected in Antarctica, radio signals are detected in Chile, optical telescopes, 42-meter telescope in Chile and a 32-meter telescope somewhere else detects something in the optical. This may all happen at the same time. We may want to go in and actually adjust the instruments in order to fine-tune it, and we want to do simulations at the same time. So we have somebody, say, here running a simulation at Caltech on the Blue Waters facility, which is a petascale supercomputing facility that's about to be deployed at the University of Illinois in the next, say, 12 to 18 months. Somehow this has to all be integrated, and people have to be notified of things. And in fact, if you're interested in this, you may know that there's an application even for your iPhone called the Transient Astronomy application that will notify you when some amazing event has occurred in the universe. And this is the kind of thing people will actually be using now to be notified of something, to bring their teams together, and then begin to do science based on those kind of events that occur. So it's going to be event-driven transient astronomy, something very new. And so the point I'm getting at is that it brings in social networking technologies that will allow collaborations of scientists around the world who probably will never actually all know each other, but somehow they need to work together to deal with this global array of instruments and simulations that need to be done. Okay, so that's all the astronomy, almost all the astronomy I'm going to talk about tonight. But I want to point out it's not only in these sort of areas of astrophysics and general relativity and black holes, but it's everywhere we see this. So here's an illustration of Hurricane Katrina. So you all have heard of Hurricane Katrina, and this is Louisiana. And these black dots are the actual locations of Hurricane Katrina at various times. And this is about 5 days out. And these lines coming out are tracks of projections of where the hurricane would go based on the different models and the different initial conditions that people had. So ultimately, what we want to do is that, well, we want to know exactly where this is going to go, but at about 3 days out, you notice all of these tracks more or less converge on New Orleans. So by 3 days out, we were highly confident that that hurricane was going to actually hit the city of New Orleans or very nearby. But what we really want to do is to be able to dynamically integrate observations from satellites, sensors that are placed across the Gulf of Mexico, and feed those into each one of these models so that we can get the most accurate, up-to-date model and even do comparisons. Say over the last 6 hours, the data are indicating this, the hurricane is taking the particular track, the actual hurricane is, which of these models is actually projecting the best path? And so that will give us an idea where the hurricane is more likely to go to reduce the uncertainties. But what we really want to do is to not only know where is the hurricane going to go, but how is the water going to respond to it? So the thing that does the most damage around the coastline is not the wind, but it's the storm surge. And the storm surge is the mound of water that's blown by the hurricanes, and it can be something like 10 meters high. So it's like almost like a tsunami, but it sort of comes in a very, very powerful way. So a huge volume of water can come in, and in fact, that's not actually covered by the models that tell you about the hurricane development itself. So what you have is different hurricane models have to be coupled to models of the storm surge, and you say if the wind is blowing like this, how will the water respond? So you have to actually couple these on different computing facilities. And then you want to know, depending on where the hurricane goes, it turns out they have different storm surge models. So for this track, for example, if it comes this way, you have to couple dynamically that hurricane model with a different storm surge model, because the models depend on the different areas of the coastline. They depend on whether it's a muddy area or a marshy area, a sandy area. It depends on lots of details of the coastline. You may have different models you have to invoke. So you have almost a combinatorial problem of matching different models with each other, coupling them to look at all the scenarios. And then further down the line, you want to know how will the levees respond if the water is going to come into Lake Pontchartrain. And for example, that's what did the damage in New Orleans, that one of the levees actually failed because of the storm surge that came through. And then you want to know, based on that, what might happen, where should you place supplies, how will people respond? So there's economic, social, behavioral, as well as hydrodynamic, as well as sensors and so on. Now, you want to be able to integrate all of this into one complex problem-solving environment. I mean, ultimately, not maybe like the master website, but I mean some way that these models and these scientists can all be brought together, and it's not something you want to do over a period of 10 years, but you have 5 days when a hurricane is coming in order to bring all of this expertise together. And so ultimately, one of our goals is to provide the kind of computing environments and the sharing infrastructure, as well as the sort of intellectual incentives, so that people are willing to collaborate so that problems like this can actually be addressed in periods of small numbers of days, not simply something like over 10 years you want to make that happen. So these are the kinds of challenges that are common to virtually all problems in computational science, computational and data-intensive science. So increasingly, you're hearing people talking not just about computational, but also to highlight the role of data, computational and data-enabled sciences. So here I've put up a number of things. Of course, this is gravitational waves, but it has to do with things like global warming, simulations in the automotive industry, fluid flow and porous media, as it's sometimes called. There's a very wonderful talk given by Tom Lang from Procter & Gamble very often about the impact of high-performance computing on the industry of diaper making and how important that is, and how, in fact, they're orders of magnitude away from being able to properly simulate fluid flow in a diaper. And so, as Tom says, they don't like to do field tests. They would much rather do simulations of these events. And so the point is, this kind of expertise is common. It's needed by all of us. And I had a very interesting conversation once with Tom, somebody from Morton Thiokol, and we were all talking about the fact that we all needed to have environments that provided adaptive meshes, and we needed to worry about interface problems between the meshes, and the problems were common to diapers, to rocket manufacturing, and to general relativity. So the point is that there is a lot of commonality. So we need to find ways to create the environments that can allow people to work together, even though they have come from very different kinds of backgrounds, and sometimes you need to integrate many different areas in order to solve a problem. I'll stress also, again, and I keep coming back to this, about data. Larry Smarr, many of you will know, Larry sort of switched his career from being a supercomputer person to a data person, and the way he said it to me, supercomputers now, from my new point of view, are merely generators of petabytes of data. And so I have to worry about the data side of this now. So that's one of the issues as well. So when all this data are being generated by either supercomputers or by experiments, something like the LSST, all of that data has to be analyzed in some way. And so again, that becomes a petascale computing problem or an exascale computing problem itself. So this more or less says the same thing that I've said before, that we need to have this idea of grand challenge communities, not just a grand challenge team, but ways to actually integrate entire communities, different communities together to be able to dynamically assemble to solve complex problems. And there's some commonality and there's some differentiation, and so getting the balance there is a difficult art, but that's really where we're going. And remembering the fact that we still need to have the brilliant individuals and even the very good individuals working together, but they have to be configured in groups and teams and communities and in sort of a multi-scale way. So the individuals can do work that can somehow be taken up by others in a more rapid fashion. And this has implications on everything, from things like data sharing and technologies and methodologies that are needed for that, to the ability to share software and even publications, thinking a little bit further down, being able to really do text search. If you wanted to do a text search for all publications in some area that, say, uses fluid dynamics of some particular kind, you can't do that now because typically you don't have a subscription, or the search engines don't have a subscription to those journal articles that are usually behind firewalls and they're subscription-based. And so there's a lot that needs to be done in order to sort of break down those barriers, in order to make it possible for people to have information and knowledge that's carried in one community represented by a particular journal to make it accessible to another one. And so but the point is that we need to think about data and sharing of data and networks and the technologies, and also the intellectual property issues that are faced as we go forward in order to solve these complex problems. So I'll just point out again the group that I used to work with, but not really anymore, now at Louisiana State University, is experimenting with these kinds of social networking technologies to keep their collaboration informed. So for example, simulation codes can actually contact people via Twitter and other technologies in order to let people know what's happening in a simulation. Have the black holes merge? Did the code crash? Did something interesting happen in it? And also to be able to post visualizations through social networking technologies, in this case Flickr, that are automatically posted to websites so that people can then share them and see what's going on. So this is sort of a crude illustration of what you can already do with today's social networking technologies to bring together the kinds of collaborations that you need. So an important aspect of all of this is that social, behavioral, and economic sciences are going to be very important as we think about how do people collaborate, what are the right incentives, what are the behaviors that we can do, or that we observe in people? How do we accommodate people's needs in order to allow them to work together? So these are research issues as well. They're not just things that if we did the right thing, necessarily people would adopt them. It has to be something that really provides incentives for people to actually adopt them. So let me just pause for a minute and kind of review what I said, which is effectively just science is being radically changed by the kinds of problems that we're faced with today. And computing levels have gone up by many orders of magnitude over a very short period of time. So I would say, again, it's been a step function with the culture of science being more or less the same for 300 or 400 years, and now suddenly things are changing absolutely dramatically at paces that have never been seen in science before. So we don't particularly know where it's going in the long term. We know in the short term that we have a lot of work to do simply to understand the amount of data and to figure out the kind of collaborations that are needed for this. But I'll just point out that if we've been doing something for 4 centuries in the same way, we still basically think like that. All right? So we have to realize that radical change that we're really facing can't be dealt with by our current incremental approach. So we have to really rethink the way people do science and the way people work and the kinds of methodologies that are needed to support complex problem solving. And I'll just point out, if there are any students in the audience here, if you remember that your professors were something like 10 to the 9th times disadvantaged compared to you in terms of the kind of computing power that you have at your disposal right now, it means that you're just absolutely in a new place and you can do very exciting things that just were impossible, I mean, not even thinkable just 10, 15 years ago. Okay, so with that, I'm going to switch gears and point out that we don't really know how to solve any of these problems at the moment. So there are lots of crises to deal with. And when I first came to the National Science Foundation about 2.5 years ago, within the first month, suddenly the world financial markets all collapsed. And this cartoon came out, and I began to think it wasn't necessarily the best time to be serving the federal government because there wouldn't be any funds to do anything. And this cartoon sort of shows, well, financial crisis, relax, I'm on top of it. But all these things are going on. And so I'll change this and say the cyber crisis. We're not at all on top of the cyber crisis because we have so many things to worry about. We have computing, data, software, networks. We have to think about how do we have organizational structures that allow people to really work together and incentivize them to do that? What are the promotion and tenure qualities that you need in order to have people want to be able to work in teams and so on? What about education? How do we educate people in this? And how do we integrate instruments and facilities? So we have to think deeply about these things. So let me give a few examples of this. So 3 crises. I'll do 3 now, and I'll do 2 in a minute as well. So let's just start with computing technology. So those of you who are at the workshop today, and a number of you talked specifically about these issues of running on machines that now have hundreds of thousands of cores. So I just want to point out that this is, again, a paradigm shift where we went over years to the number of processors being something like 1 for a long time. That just got them faster and faster, and then maybe 2, 4, 16. But now, then it was 256, then it was 1024, then it was, we're up to literally many hundreds of thousands. So we're now heading towards millions of cores. And so if you now think back to like early days of microprocessors, it seemed amazing. You could have 100,000 transistors on a single chip. So we're now at the level of having to design scientific computing codes that has the level of granularity of processor cores, which is the same as the number of transistors that you had in your original microprocessor. So you have to think about completely new ways of doing it because you never thought about sending one bit of information from one transistor to another. You didn't have to program at that level. And so we have programming paradigm issues here, as well as fault tolerance. If you have 200,000 sort of moving parts, they're not actually moving, but actually some of them are. You may have disks. Some of them are going to be failing, and so you better think about your simulation codes or your applications to be very fault tolerant and when that happens. And of course, there are new technologies coming all the time, very, very sophisticated new technologies, and so it is not clear in what direction this is going to settle in a few years. Probably there'll be multiple places that we go at the same time. So the point is, there's a lot of work to be done fundamentally at the basic computer science research, as well as the computational science research of how you would use this, as well as how this maps onto the applications. I talked a little bit, and I'll focus a little bit more on this as I finish my talk, on data, provenance, and visualization. But the key point I want to make with this bullet is that we're generating more data now every year than we ever have in all of human history combined. And so that's a sobering thought. And then software. Of course, all of this technology is absolutely useless without software. So at NSF, we're trying to take notice of this, and we're looking at investing, I'd say over a period of a decade, probably hundreds of millions of dollars in software activities, because software is really becoming the modern language of science, engineering, and of research, and even of society in many ways now. And so it's something that we have to take much more seriously. And these codes, of course, that people generate have millions of lines, and an error in any one of them could lead to incorrect results. So you have to think very hard about, is your science actually reproducible? In fact, how would you validate the results of a simulation that maybe took some data from some satellites and that maybe had subroutines or modules that were written by collaborators across the planet, and then you want to be able to reproduce that, say, 6 months later, when basically, 200,000 of your 3 million lines of code have somehow changed? Can you really do that? So I'd say we don't even really know how to track these things at the level that we need to with the complexity of the environments that we're dealing with. We really, I think, don't know how to reproduce results. And so there's a lot of research to do there. So it's kind of a scary environment, actually. So this is a graph that I borrowed from Chris Johnson at the University of Utah that points out how much data are being generated in terms of billions of gigabytes across the whole planet. So I'm not sure how this is all estimated, but I'll take it for what it's worth. And so it shows that in time, we're generating more and more data. And of course, this is the amount of unique data that's been estimated that we generate in any particular year. And it happens that around 2005 or 2006, it's estimated that we started generating more data in any given year than we had in all previous years combined. So that means every year we generate more data than have ever existed on the planet up to now. And so this is, again, a new problem. We don't have the physical capacity to store all the data, by the way. So there's a big question. What data do you want to keep? What data do you not want to keep? How do you tell? And so on. So again, the problems of data management itself are, I think, theoretically challenged, but even understanding the basic algorithms of how we would actually find the information in the data, the information that we want, in a reproducible way, we have a lot of work to do there. So there are many, many reports that just point out that we have a crisis in data. So I won't go into this, but I'll only say here, Wired magazine actually proclaimed it was the end of science as we know it, because theory and experiment are still perhaps important. They were even arguing they might not be, that we would just look for correlations in huge amounts of data. And it's a fair question. If you generate a lot of data from lots of experiments and observation stations and from supercomputers, are there any algorithms that could help you derive physical laws or biological laws from that data in the way we take it now? I'm not sure that there are. So we have to think about that. So these trends in data are everywhere. And I want to point out, so one thing you always hear about the LHC, the Large Hadron Collider, there are over 10,000 scientists. They're not doing 10,000 experiments. There are 6 major experiments, actually 2 of the big ones, and there are a number of others. But basically 2 major experiments competing with each other, and there are 10,000 or more scientists working across 3 dozen countries, generating something like 25 petabytes of data. So that community has begun to really think about what you do in order to distribute that data. So there are data that are distributed, generated from the Large Hadron Collider across many sites across the world, and they have a sort of hierarchical scheme of how they manage that, how they track if something has changed. So they're tracking the provenance of that data, as we call it, how it changes as it moves or as people do things to it. So that's very important. We had a workshop at the Mathematical and Physical Sciences Directorate last year at NSF, where on data-enabled science, and every area of science highlighted huge challenges, whether it's astronomy, physics, material science, chemistry, also mathematics, as the division of mathematical and statistical sciences, is very concerned, not that mathematicians generate that much data, but they see it as a very rich playground to generate new mathematics. So they're very interested in this as well. So we have many examples. We heard earlier today some talks about biology, DNA sequencing. So in comparative metagenomics, you're looking at DNA sequencing entire families of thousands of organisms. And in fact, already today, there is a machine you can buy that an assistant professor with an NIH grant could buy that generates a terabyte of data per minute. So that's the raw data. So it's usually processed, and the output is finally not that much. But the point is that you have in individual laboratories, if you sum that up over periods of order a year, it's like an LHC in an individual biologist lab. And there are a lot of biologists out there. So watch out. Data are really coming. Petascale to exascale simulation, they generate peta to exabytes. And I'll just say again, this Large Synoptic Survey Telescope will generate an entire Sloan digital sky survey every single night. And so we're going to be looking at real-time connections between simulation and observation from observatories around the world, and somehow we have to move all of that data around to make sense of it. So when we do that, I think this is a problem that is not highly recognized enough by the community now. What happens as data are moved around or as people touch it, people add to it? Is the data described properly? So here's an example, which I borrowed from Giuliano Friari from the University of Utah, of a Nobel Prize-winning notebook that pointed out some important things. So when were the data collected? So 19th of June, 1946. Okay, so that's it. You need to know when something was collected. You need to see the data. It has to be in some reproducible form. It's been digitized now, so it's on my PowerPoint slide, so that's a good step forward. It has to be annotated in some way. So hooray, there's been a great discovery. Now, it's kind of straightforward if you do that in a notebook, but if you're doing that where you have thousands of collaborators collecting data from many sources and it's about one scientific problem, including millions of lines of software, what's the provenance of that? How does that change as you go from one state to another? Or as your computing system changes, or if you use multiple computers, even changes in the operating system or compilers can often change things in unpredictable ways. So you have to be very careful about this. So I would just say that we have an issue there that we don't really know how to solve right now. How do we really deal with the data as it's moving around? So let me talk briefly about two more crises. So those were the first three crises, which were software, compute, and data. Okay? But now let's think about, what about the organizational challenges of how we enable people to work together? So universities are really struggling with this. I struggled with this a lot at Louisiana State University, building a center that actually had faculty jointly appointed with across 5 different colleges, 13 different departments. There are many issues of language, promotion and tenure, culture differences, and so on, as well as scientific differences. But one thing they all had in common was computing problems. And so there is something to that. But how you actually make that work in a traditional academic environment is very difficult. So for example, in my center, we had a criterion for success. How many multiple author papers do you have? So then you go home and you talk to the department chair in computer science. He tells me, we want to know how many single author papers does your joint faculty member have. It's exactly contradictory to where we're trying to go. And so these cultures take a long time to change. And so we have to think about that. And so there are these recommendations from this thing called the PTAC report, the Presidential Information Technology Advisory Committee from 2006. That talked about computational science, ensuring America's competitiveness. And so some of the top-level recommendations are, number one, universities must significantly change their organizational structures if they're going to remain competitive in global science, particularly how you support multidisciplinary and collaborative research. So I think we don't know how to do that. I think what's going on here in Abu Dhabi is a good example of a greenfield start. Let's see if we could start a new structure associated with the traditional university, but are there new ways of doing science that are more aimed at the challenges we have in the 21st century? So I think that's very, very, very important. And then just the second point was that simply pointing out that computational science, which has really emerged as a discipline in itself, is something that is not very well supported within the federal government. So that's one of the things that I have a role now at to try to do it in the U.S., is to figure out how to support these kind of things, given the fact that we also have structures in our funding agencies that parallel the universities. We have a division of chemistry, we have a division of physics, we have a division of mathematics, more or less along the lines of the way universities are structured. And so it's not always easy to figure out how to do this. And then finally, the other crisis is that this computational infrastructure, cyber infrastructure environment is running away from us on exponential growth paths, and yet we're still teaching things the way we did for many, many decades, if not centuries. And so how do we develop a workforce to effectively work in this world, and how do we develop universities to help support that? So I think they're big questions. So let me illustrate NSF's vision for handling this in a cartoon. And so in effect, we have deployed a number of supercomputing centers that we, in this language, are called Track 2 centers. So they're sort of small supercomputers of order $30 million apiece. And then there's a very large one called Track 1. This is a bit of a pyramid here. And then there are campuses that, of course, have smaller scale computing facilities as well. And Track 1 is the very large $200 million level supercomputer, in this case at the University of Illinois, the Blue Waters machine. And so one of the challenges is, how do you provide a coherent environment that takes you from campus to medium scale supercomputer to large scale supercomputer? But you need to have these environments to solve the problems I've been talking about, but you also need to make sure that they're properly synchronized so people can effectively work together. So that's a picture of the Blue Waters facility going in at the University of Illinois. We also then remember that there are networks that connect these things. Typically, at least in the US, networking is done independently of the funding agencies, more or less. To some degree, we fund it, but it's been done more or less by the private sector, by universities, by National Lambda Rail or Internet 2, different organizations working either in competition or together. And then we're also beginning to understand the need for data. So we're making a lot more investments in data in terms of developing a data services architecture that will serve the national and international communities. And we need to be thinking about this in the international context. So there's no question about that. So we are doing that. So I point out here, in this entire picture, this is to illustrate that there is still now many assistant professors in biology buying machines that are generating terabytes of data. So they're not just coming here, but they're actually being generated on campuses all over the place. This is completely overwhelming campus networking infrastructures. So we have to think about, how do we actually build the campus of the future? I think, again, what you're doing here will be a great example that we can all learn something from as you make investments come from the ground up in brand new cyber infrastructure to support this kind of science. And then something that's always been done independently and separately are these large-scale facilities. So there are radio telescopes, the LHC, the LIGO detectors, and so on. These are projects that are $500 million to $1 billion. That's a lot of money, and a lot of that money usually goes into the cyber infrastructure. Typically, it's been done on a one-off basis. So LHC does its, ALMA does its cyber infrastructure, LIGO does its. We really can't afford to reinvent cyber infrastructure at the level of hundreds of millions of dollars per project. So we need to think about ways to integrate and provide a more coherent approach. And so we're working hard on figuring that out. And again, I'll just come back to the environment that a graduate student finds himself in right here. So as I particularly try to illustrate, it's not just that you need to use a supercomputer. It's not just that you may need to use a remote data sensor or something like that. You need to integrate this to solve your particular complex problem that today's graduate students are finding themselves being handed. So it's no longer adequate to just do what my advisor did to me, was to said, here are Einstein's equations, go code these up. I got some time at the Pittsburgh Supercomputer Center. You'll just figure that out. Now you spend most of your career on the latter part. Einstein's equations have already been given to us. The rest of it is figuring out how to solve them. And that needs a lot of attention. So how do we educate people in that environment? Okay. So there are recommendations, and I'll kind of close out my presentation here talking about the recommendations that people have been making and how we deal with them. So in particular, I'll come back to the PITAC report just to highlight this. And it says, computational, and I've ad-libbed in here, and data-intensive science, the use of advanced computing capabilities to understand and solve complex problems is critical to scientific leadership. I'll come to this in a minute, to economic competitiveness and to national security. So it's one of the most important technical fields of the 21st century. And it's essential to advances throughout society as well. By the way, in the data overload, I think I might mention this in a slide later, but I just read somewhere that in the US mobile phone system alone, over 1 exabyte of data were delivered in the last year. And now we're talking about society also generating data levels that are far beyond even where science experiments are. And so it's not only in these sort of singular events. So what is needed? So NSF is working hard now to take all of this input and particularly to try to integrate with the different directorates within. So the Directorate for Mathematical and Physical Sciences, Biological Sciences, Geosciences, Computer Science, Office of Cyberinfrastructure. We are now working together much more closely than we ever did before to think these things through. And we basically have these same things that I've been saying all along, but not taken in isolation. So high-end computation, data, and visualization, the more traditional supercomputing type activities, thinking about this now with an eye towards sustainability and really valuing the scientific expertise that's needed around those centers. So it's not just the computer, but the most important asset at an HPC center is the people and the staff that are built up around that. So we have to have ways to actually fund these facilities in a competitive way that values the sustainability of the staff and the scientific expertise, and also in a way that provides the ability for them to innovate, not just to provide cycles, but really to innovate, to provide that innovation that we need for science. So we're thinking about that a lot. And if you're in the US and you're looking for new solicitations, as you know, we're under a continuing resolution right now, but in the last solicitation, you will have seen a couple of small steps towards that, and in the future ones, you'll see more. At least I hope so. We're working on that. So MREFCs and collaborations, these are the large-scale facilities, thinking about how they are integrated into this, putting software on a first-class basis so that it's no longer just something you have your graduate student do, but really support software that can last for decades while supercomputers come and go over a period of 3 years, thinking about how you better support that, how you integrate in campuses, but most importantly, supporting the people that do computational and data-intensive sciences. So those are the sort of the pillars of our thinking now. And so you might have noticed, if you haven't seen this, if you're not in the US, there was what we call a Dear Colleague letter in the language of NSF that was released in December of 2009. The important thing about that letter is that it was signed by every unit at NSF. So that's the important thing. It didn't say very much, but we were trying to send a signal that we are under the covers here thinking a lot about this. And I'll just say that there's more coming, and you may see in the President's budget request, which will be released next month, some evidence of that. So that's all I'll say. So we had a lot of task forces. A number of you have been helping advise us within NSF what we should be doing. And these task forces have basically completed. So we thought about how we connect to campuses. What do we do about software? How do we train people? What about the science activities that drive all of this? The computing environments and the data and the visualization. So there are many reports that have come in. They will be available on our websites. Some of them are already there in preliminary form, but within the next month or two, they should all be available, and I would encourage everybody to watch out for those. But I'd say perhaps the most important recommendation that came from these task forces is that the National Science Foundation should create a program in computational and data-enabled science and engineering based in and coordinated by the Office of Cyberinfrastructure, and it should, however, be collaborative with all the other programs and the other units. And so this came in unanimously in a sort of a longer form, endorsed by the advisory committee, signed by the outgoing director, Arden Bement. So this is sort of a central piece of our thinking now that we're thinking as we go forward. So let me just close out here in the last few minutes. I want to talk a little bit about data again, because I think as I said, science, not only science, but society is now becoming data-dominated. There's a new book out from last year, or maybe 18 months ago, called The Fourth Paradigm, edited by, in particular, brought together by Tony Hay from Microsoft. And I just want to point out, it's not just about science, it's science and society. There's no question about it. But there are many kinds of data. I would consider software a class of data. Increasingly, publications can not only be digitized forms of traditional publications, but they may be data sets. And we have to think about how do we actually peer review those, or should we peer review them? In some communities they do. How do we actually cite them? How do we curate them over time? And so on. So libraries will be much more important in this area than they have been in high-performance computing world in the past, because I like to give the example. When I was a graduate student, I did my PhD thesis at Yale. It was done in Microsoft Word, actually. It had a little 3.5-inch floppy disk, and I can't read that now. But at the Yale Library, there's a Gutenberg Bible that's been readable for 500 years or something like that. So librarians have a much better idea about how long things need to be kept than computer scientists do. And so I think the libraries are going to be important repositories for digital data. The Johns Hopkins Library now actually is the repository for the Sloan Digital Sky Survey. And so they're actually curating that as one of their collections. So the point is that publications and data become the medium for collaboration, and in particular for multidisciplinary work, for people to be able to come together. So we need to find ways and tools for people to access all of this data. So fundamental questions then are focused around data as we go forward. How do we remove boundaries between disciplines? If you could share data between disciplines, if it were made available, and if the scientists felt it was in their best interest to make it available, why would they do that? Not because of the goodness of science, or they'd like to do that, but because they'd like to get some kind of intellectual credit for that. And they'd like to be able to get promoted and get tenure because their data set was used by everyone else. That would be important. So we're, in some fields, we're beginning to look at that, but haven't gotten very far. So how do we incentivize sharing of data? And how do we attribute credit for this new publication form? How are they peer-reviewed and so on? So what even is a publication in the world going forward? It's something different. So as the first part of this, at NSF, we have now instituted a change in the way we implement the policy. So we've had a policy for a long time at NSF that says investigators are expected to share with other researchers at no more than incremental cost and within a reasonable time the primary data that you generate in your research. Now, every one of these things has large asterisks, like how long is a reasonable time? What is the primary data? What do you mean at incremental cost? It could cost millions of dollars to provide this data in some form to my peers. And do I have the money or the incentives to do that? And what do you mean by expected to share? My grant runs out in 1 more year. What are you going to do to me if I don't share the data? So there are many, many implementation questions there. So we have now said, as of I think it's next week, you will have to submit a data management plan as part of any proposal to the National Science Foundation. So we're recognizing that data is very important, but we're not saying that you have to share the data, and we're not saying that you have to make it available. We're only saying that you have to put together a plan, and that plan will be peer-reviewed. And so we just want to open this up and make people start to think about it, have the community look at it. But if you don't put together a good plan, then your peer reviewers may say that you should do a better job with that, and that can come back. So it's the process of letting the community sort of tell itself how we should begin to take care of data, but not to force any particular idea on this right now. So we're just going to require the first step now. The next thing I'll say is just that the National Science Board that oversees science policy at NSF and more broadly than that is beginning to examine all aspects of data, whether it's how do we access it, what about publications, and so on. So that's coming. All right. So the last couple of things I just have on innovation. I wanted to just talk a little bit about the innovation economy and how important that is. So all of this has been about computing and applications and science, a little bit about society. And I just want to come around to the last step in this. For a lot of reasons, some areas in the U.S. in particular have become much more advanced economically because of advances in computing, particularly the Boston and Silicon Valley areas, as we know. And there are particular reasons that's happened, and in particular because universities had built up very strong programs in those areas, and then around those innovation hubs would develop industry and companies and so on. And so just to quote Carly Fiorina, former CEO of HP, where do we put an HP facility? We go where highly skilled and creative people are. So universities can play that role, particularly as we go forward. Companies are needing to figure out how do they bring together a multi-physics simulation framework for diapers, for example. I mean, so they need to have people with expertise in parallelization, visualization, numerical methods, et cetera, et cetera. So they can find them around universities that make these kinds of investments. Creating an environment of global leadership and innovation, we have to do this around investments in research centers. I just want to point out, this is not a new idea. I mean, at least in America, it goes back to Thomas Jefferson, probably goes back to, Aristotle or something way before that. But Jefferson actually wrote that knowledge products show infinite expansibility. They don't get used up. And talking about developing the economy of an early developing country, he was talking already about the knowledge economy back then. So again, fast forward several hundred years, you have the Council on Competitiveness looking at case after case after case of how Innovations in computing can have direct consequences in economic development. They enable breakthroughs in research and development and production. They shorten the development cycles for getting products out, and they increase the ability of people to stop having to prototype things, but to do things virtually through simulation. And increasingly, it's important for these companies not just to simulate things, but to analyze all of the data that they have. And so again, it's coming back to data. So just to bring it really down to earth, from like cosmic collisions of black holes to golf clubs and potato chips, again, Procter & Gamble, doing simulations. If you know, Pringles all have a sort of a similar shape. You know, they're packed in these cans. They're put on conveyor belts when they're made, and they go into the can. But if they go too fast, they sort of get air. They get a little lift, and they can fly off the conveyor belt. So they've actually used fluid dynamics simulations to better configure the conveyor belts that send potato chips into these cans. And so it's something very, very practical. But again, it comes right down to things that I used to do in my career of simulating black hole collisions and so on. So I think I'll just have a couple of comments here. One of the problems that businesses said why they don't use computing environments more systematically is the dearth of computational scientists. They can't find them, so we need to train more of them. It's important for not just science, but for science and society and economic development as well. So I know I've gone long, so I think I'll just summarize here. Critical lessons to take home, as you've heard me say at least 20 times tonight, science and society are profoundly changing by many orders of magnitude over the last 20 or 30 years, and after many, many centuries of things not changing very much. So it's really a step function. And I think universities should be seen as community anchors for innovation in this world, because it is changing so rapidly, and a lot of the new ideas are coming out of universities. So how to build that into economic development is something very important to be thinking about. And then data-intensive science, not just HPC, is increasingly dominant. And I would say, a little bit to my surprise, when I came into math and physical sciences at NSF, HPC was important to some groups, but data overload was important to everyone. Every science area, it was the one thing that resonated. So we're thinking a lot about how academia and agencies and also companies, how they can address this. And I think I'll just stop there, and thank you very much.
Hi, I'm Sohan D'Souza, research engineer with Masdar. How does it currently work with the ownership of the data? If say the NSF or some funding body funds research, now procuring data costs money, often either in the effort put in and the time put in, or sometimes just buying it off, for example, mobile phone networks. So what happens in this case? Does the funding body own the data, or take ownership, or does the researcher own it, or? No, so typically the university may have, depending on their own intellectual property agreements with faculty, the university sometimes has ownership of it. The NSF, the funding agencies, at least within NSF, I don't know of any cases where the NSF would feel like it owns the data. On the other hand, there's increasingly an awareness of the fact that publicly funded data should be made available to the public. And so we want to provide requirements that data are made available over time. I mean, I think there's some communities that are very ready for this. There are other communities that are not at all ready for this. So, for example, the high-energy physics community that I mentioned, they're very advanced in terms of handling large amounts of data. But they're not making it available immediately because some people spent 20 years of their career just preparing for the LHC to turn on, and they're not ready. You know, the Atlas and CMS experiments are not going to give their data to each other right away. So there are cultural issues that have to be dealt with. So we wanted to deal with that sensitively. But ultimately, we're trying to move in a world where the data are to be managed and curated and then made available to others. So that's the direction. And we recognize we'll have to pay for that.
Just a simple question, actually. Thank you very much indeed for your insightful lecture. Do you think there is a clash of interest between disciplines because of, in collaboration, when they collaborate in projects such as these? Do you think there might be clash of interest between, say, physics and social sciences, or just a question which probably is very crude, but Um, will there be a clash of interest, or is there a clash of? That's one thing. The other thing is, do you think that we have to fight for the prevailing wisdom, which perceptions always are more important than reality? Do you think we have to fight this notion of ingrained perceptions of traditional means of thinking with the new thinking of what you presented to us today? Thank you.
So I think the first question was about the clash of cultures, particularly between, let's say, social scientists and physical scientists. And so we're experimenting a lot with that right now at NSF, because we're talking about a thing called SEAS, which is Science, Engineering, and Education for Sustainability. So it's a new sort of set of programs that we're developing over time. And that includes economic and social behavior quite strongly, and that's considered a centerpiece of this. And so although we know it's important, we often find when we get the scientists and the social scientists together, the communication is not there. And in particular, the physicists, I'm a physicist, so I can say this often, think, well, why do we need the social scientists? But then you realize you don't know how to collaborate necessarily very well. So there's the science of collaboration, and that involves social behavior. And also, if we're thinking about things that are important for the climate or for the environment, for economics, we have to understand how people will actually adapt, how they will take up new developments or new technologies as they're actually created. And so increasingly there's an awareness. So it'll take some time, but I think we're moving in that direction. In terms of, I think the second question was more about incentives to get people to change behavior, let's say.
To have a parameter shift and think in innovative ways.
Right.
Yeah.
Well, I mean, particularly when it comes to sharing of data, some communities are really ready to do it and actually do it very well right now. And others, I mean, in my own numerical relativity community, I would say it's something that's not been taken very easily. I spent a lot of my career trying to convince my colleagues that we should share software. And bit by bit, in the last 10 years, it's been happening. And now, I gave that example where there's a collaboration of about 60 scientists around the world that are actually sharing it, but they do it in a particular way. So there's a framework that they agree. There's certain things that are shared, and then there's certain things that they develop themselves, where they use the common things, but then they differentiate it and with their own special things, and then that way they can take some value from it while also do something that differentiates them. So it's not like everyone's using the same code. And then in time, people then decide that they're willing to make that available. So there's a trend in this direction. It's going at different rates in different communities.
I guess I have a question. And you've been describing a massive shift in ways of doing science and in general, and thinking of the future as being so different from the past that everything has to be questioned. And in fact, you gave us a good incentive to say, if you have the possibility of starting new, how would you really start it? Which is exactly why I'm here, by the way. But so then the question I have, how do you see NSF's role in changing that? And how do you see the role of universities really changing that in the context of what has been a pretty deep level of structure, like departments, like the tenure process being the way that it is, counting how many times you're either on the front or on the back of a paper in some disciplines, right. And silly things like that. How do you think NSF can play a role in helping that change?
So I love the question, because I've thought about this for a long time. Now that I'm at NSF, I'm finding it's harder than you think. Perhaps you're not really in control of that much, but we're beginning to really talk a lot more with universities about this. And I think NSF in particular has a culture that's different, say, from the Department of Energy, where we are much more ground-up driven. So a lot of people within the foundation actually think we shouldn't tell our scientists what to do, we let them tell us. Where the Department of Energy would say, we're going to do exascale, something or other, and they've made that as a mission that they're going to do that. I think you're going to find more leadership coming from NSF to help universities do these things, but not in a very draconian way. I think what we'll do is begin to have more things like forums where we really discuss what's the future of the research university. We will fund people to come and talk about that, and we will point out these kinds of things. And we may do things like say, have you noticed that you need to have more people working together and you need to have these new data environments and so on? here is some funding for you to rethink your own campus environments in the face of all these changes. And then, but we want to make sure that university provosts and deans are actually engaged in that process, and department chairs and so on. So these are the kinds of things that we're thinking about doing.
Right.
And you'll probably see programs like this coming.
Well,
up.
NIH, for example, started this program to sort of establish new things in terms of what is a PI, right? So you don't have, this co-PI, for example, is considered lesser within an academic unit than maybe it's meant to be, because if you're a co-PI, it means that you can't do the project without all of the people involved.
Right.
Whereas in some circles, that's not considered so high. So they changed that structure and they talk about multiple PIs. They don't talk about co-PIs anymore. So they have a dual PI structure and so on and so forth. So I guess those are some of the mechanisms which can be used by a funding agency to help the evolution of academia. Yeah.
So here's another example. So we haven't done this yet, but we've been toying with an idea like if you apply for an NSF grant, you have to say, what are your 5 most important publications and 5 other publications or something like that. So what if we said, what are your 5 most important data sets? People would, first they'd say, you know, what? And then they'd say, well, wait a minute, you know, I'm supposed to have a data set? You know, and you know, you could do little things like that. That would seem innocuous, but they could have really large change.
Absolutely.
Like I think the data management plans. I'm getting a lot of emails from people out there saying, what are we supposed to put in a data management plan? You know, but now they're really beginning to think about it.
Sure.
I think what I heard today was more probably relevant to data, as in sort of numerically intensive analysis of large, complex sets of data. But one of the challenges, especially for working across different disciplines, is turning that data into knowledge.
Right.
And nowadays, for example, if I'm looking for a source of knowledge, I go to Google, do a search, or I go to Wikipedia and find that knowledge. And that is actually as a result of quite a lot of collaboration, which is outside just purely the university and academia. Do you have any thoughts about, I mean, you mentioned obviously the use of technologies like Twitter and Facebook or Flickr, etc., for sharing and this information, and how do you think that NSF can actually support or be part of these activities?
Okay, so sure. There are a couple aspects to that strike me. One is, for example, I talked about the big sort of eye-catching generators of data, but not so much about the kind of thing that you might have 1,000 chemists that all have some kind of data of materials properties or something like that. And so how do you find some way to harness all of that and then provide information that's kind of cuts across? And so we are thinking about those kind of things, and interoperability even at small data sets, and how you would actually provide them. If every professor puts up some data set on some website, that's of some value, but it doesn't really help harness the whole collective power of it. And so we are thinking about that, and also at the level of things like publications. I think there's this idea that if you could actually have publications that were searchable, completely searchable and open, you could develop algorithms that could help you actually follow arguments from one paper to another to another. I mean, machine learning type algorithms or other things we haven't even thought of yet. And so again, it's making the things available first, but then thinking about not only finding features in huge amounts of data coming out of some big, you know, LHC, but how do you collect it across? And so yes, I mean, the answer is yes, we're thinking about that, but mostly we'll try to incentivize the scientists to think about that.
So maybe it's a little bit related, Ed, but when you talk about the data management plan, I would imagine that quickly people will say, well, I need tooling to do this. I need annotation. I need common dictionaries for determining, you know, when I say what something is, what it means, so it means the same thing to somebody else. Are there NSF programs being developed to, you know, sort of calls for creating that tooling that would then, for the guy who now has to have a plan, he says, well, I'm going to use that guy's tooling?
So that depends on communities. So there are communities that are already rather advanced in this, and so people will say, okay, I will conform to that particular community. It happens, for example, I'd say this isn't exactly a coherent community, but in Antarctica, there's by treaty, that data that are generated on science experiments in Antarctica should be shared across disciplines and across countries. And so people are dealing with that in different ways. But because of that, there are some sort of norms that are emerging in some fields in Antarctica in particular. That's one I'm familiar with. In the geosciences, there's much more understanding of what are the kinds of formats and the metadata that are useful, and that's beginning. In some areas, like in numerical relativity, to pick my own example, it's much less understood how that would be done, what's relevant. Although we haven't had data that's been very relevant for science. It's been more or less debugging codes and developing numerical techniques and so on. But that's changing, so it depends. So yeah, we have thought about, now that we've got the data management plan requirements starting next week, in the next year we'll start working with communities to look at what are best practices and then find ways to kind of promote that back to help people figure out how to go forward.
With that, I'd like to thank our speaker again for a wonderful, stimulating talk.